On the morning of August 22, 1986, a government health worker driving toward the village of NYOS in northwest Cameroon encountered the first body on the road outside town. Then another. By the time the vehicle reached the village itself, the dead were everywhere. In their houses, in their yards, on the paths between compounds. The livestock were dead in their pens. The birds were on the ground. The crops were standing. The buildings were intact. There was no fire, no flood debris, no structural damage of any kind. The lake above the village was still. The water was an unusual reddish-brown color, but it was not overflowing. Nothing about the physical environment explained what had happened to the people in it. It would take days before researchers could confirm what had killed approximately 1,700 people in a single night. The cause was the lake itself, not through any force that moves and destroys as it travels. No flood, no tsunami. The lake had exhaled. A body of water sitting quietly in a volcanic crater had released a cloud of carbon dioxide dense enough to displace the oxygen at ground level across a 25-kilometer radius in the dark, while the villages around it slept. No wave, no warning. For most of the people who died that night, no interval between sleep and death, long enough to constitute a moment of awareness that anything had changed. Lake NYOS occupies a volcanic crater in the Oku Massif of northwest Cameroon, part of the Cameroon Volcanic Line, a chain of volcanic features extending from the Gulf of Guinea northeast into the continent's interior. The crater is steep-walled, roughly circular, and sits at an elevation of approximately 1,090 meters above sea level. The lake is deep relative to its surface area, maximum depth around 209 meters, surface area approximately 1.6 square kilometers. These proportions matter. The lake is meromictic. In most lakes, seasonal temperature changes drive vertical mixing. The surface cools in winter, becomes denser, sinks, and displaces the warmer water below, producing a full turnover that oxygenates the deep layer and prevents stratification from becoming permanent. In meromictic lakes, this process does not occur. The density difference between the surface layer and the deep layer is large enough, maintained by differences in dissolved mineral content, temperature, or both, that the two layers do not mix. They remain permanently separated. The boundary between them is called the chemocline. Below the chemocline at Lake NYOS, volcanic seepage through the lake floor had been dissolving carbon dioxide into the water for decades, possibly centuries. CO2 is highly soluble under pressure. The deeper the water, the greater the pressure, and the more gas the water can hold in dissolved form before it begins to come out of solution. This is the principle described by Henry's law. At constant temperature, the amount of gas dissolved in a liquid is proportional to the partial pressure of that gas above the liquid. At 200 meters of depth, the water pressure is approximately 20 atmospheres. Water at that depth can hold far more dissolved CO2 than the same water would hold at the surface. The deep layer at NYOS had been accumulating CO2 for long enough that, by 1986, concentrations had reached a level approaching saturation. The chemocline was holding. The stratification was stable. Nothing at the surface reflected what was building below. The lake was a pressure system, waiting for a disturbance it did not need to be large. On the evening of August 21, 1986, something disturbed the stratification at Lake NYOS. The precise trigger has never been definitively established. The leading hypotheses include a small landslide from the crater wall entering the water, a minor seismic event, or a sudden drop in surface temperature altering the density profile enough to initiate overturn in the deep layer. No evidence conclusively points to one over the others. What happened after the trigger is better understood. A volume of CO2-saturated deep water began to rise. As it rose, the pressure on it decreased. As the pressure decreased, the dissolved CO2 began coming out of solution. The same process that produces bubbles when a carbonated bottle is opened. The rising gas reduced the density of the water column above it, accelerating the upwelling. The acceleration brought more supersaturated water into lower pressure. The degassing intensified. The process became self-sustaining in seconds and could not be stopped once it had begun. The CO2 released at the surface was cold, dense, and odorless in pure form, though witnesses who survived the edges of the event described a smell variously characterized as gunpowder, rotten eggs, or something unidentifiable, likely trace sulfur compounds carried up with the gas. The CO2 formed a cloud that, being denser than air, did not disperse upward. It flowed across the lake surface and down the slopes of the crater into the valleys below, following the terrain, filling low ground the way water fills a basin. The eruption lasted somewhere between 15 seconds and several minutes. Estimates vary based on the accounts of the few survivors close enough to the lake to have witnessed any part of it. A wave was generated on the lake surface, reaching a height of approximately 25 meters at the crater wall based on watermarks left on the rock. Vegetation was stripped from the crater rim on the side facing the primary outflow direction. The CO2 concentration required to cause loss of consciousness in humans is approximately 10% by volume in air. At 20%, death from oxygen displacement occurs within minutes. The cloud leaving Lake NYOS carried concentrations that, in the first kilometers of travel, were estimated at close to 100% CO2. At those concentrations, exposure is measured in seconds, not minutes. If the kind of history that gets erased, documented in full, then filed and forgotten, is the kind you want more of, subscribe. Every episode on this channel covers disasters that were understood and then set aside. The cloud moved downhill. Gravity and terrain determined its path more than wind did. The CO2 was dense enough that it behaved less like a gas and more like a liquid in its early movement, flowing into valleys and drainages, pooling in low ground, spilling over ridgelines only where the volume was sufficient to fill the depression below before continuing. The villages around Lake NYOS are not on flat ground. The crater sits in mountainous terrain, and the communities that had formed there over generations had settled in the valleys and on the slopes that made agricultural life possible. Those same topographic features, the valleys that channeled water for crops, the low ground that moderated temperature and protected from wind, were the pathways the CO2 followed as it left the crater. The direction of primary outflow was southeast, toward the NYOS River Valley and the communities of NYOS, Cha, Subum, and Fang. A secondary flow moved in other directions at lower concentrations. The cloud did not travel in a single uniform mass. It spread, thinned at the edges, concentrated in depressions, dissipated more slowly in enclosed spaces than on open slopes. Witnesses in the outer perimeter of the event, in locations where concentrations were non-lethal, described a white mist moving low across the ground. Some described a sound from the direction of the lake before the mist arrived. A low rumble, a rushing noise. Descriptions varied. The interval between the sound and the arrival of the gas was short enough that it provided no meaningful opportunity to respond. At concentrations sufficient to cause death, there was no smell, no visible warning, and no pain. The mechanism of death from CO2 asphyxiation at high concentrations involves rapid loss of consciousness before any sensation of suffocation becomes conscious. The body's respiratory drive is triggered by rising CO2 in the blood, not by falling oxygen. At the concentrations present in the cloud's core, blood CO2 levels rose to incapacitating levels before the victim could register discomfort. The cloud traveled at an estimated speed of between 20 and 50 kilometers per hour. It reached the nearest settlements within minutes of leaving the lake. It extended 25 kilometers from the crater before concentrations fell to non-lethal levels. The people in those villages had been asleep for hours. By the morning of August 22nd, the CO2 had dispersed. Morning winds at higher elevations had mixed the gas with ambient air and diluted it to concentrations that were no longer immediately lethal. The valleys below were accessible to those who approached from uphill, from directions the cloud had not taken. The first reports reaching Wum, the nearest town with administrative presence, described roads lined with dead cattle. Cameroonian military and government officials who drove toward the lake encountered the same. The animals were not clustered. They were distributed along paths, in fields, beside compounds, in positions that showed no flight response. Some were found standing, held upright by the rigidity of post-mortem muscular contraction, as though the death had been too fast for the body to fall. The village of NYOS, closest to the lake, had an estimated population of between 800 and 1,000 residents. The number of survivors from NYOS village itself was in the dozens. The specific count varied across early reports. Documentation was complicated by the fact that household registries were incomplete and some community members had been elsewhere on the evening of the 21st. Village of Cha, several kilometers down the same valley, lost the majority of its population. Fang and Subum, further along the drainage system and at slightly different elevations, had fewer dead. The cloud's concentration had diminished over distance, and some residents survived exposure to lower concentrations, rendering them unconscious, but not fatally. Total confirmed deaths across all affected villages reached approximately 1,700. Some estimates, accounting for residents who may not have been registered, place the figure closer to 1,800. Around 3,500 cattle died. Birds were found on the ground throughout the affected zone. Insects that would normally have been present at dawn were absent. The houses were structurally intact. Gardens were undamaged. Cooking fires had burned down normally. Nothing in the physical environment of the villages, apart from the bodies, indicated that anything exceptional had occurred. There was no flood debris, no ash layer, no damage pattern consistent with a pressure wave. The objects people had been holding when they lost consciousness were where they had fallen. Several survivors in the outer perimeter of the cloud gave accounts in the days after the event. One was a man who had been attending a funeral vigil in a village on the edge of the affected zone, awake, not asleep, when the mist arrived. He described a strong smell, a sudden dizziness, and then waking on the ground hours later, surrounded by people who did not wake. He had lost consciousness and survived because the concentration at his location had not been sufficient to kill him before natural respiratory function carried him through to morning. The accounts converged on the same sequence: a sound from the direction of the lake, a mist, then nothing. The speed of onset left no interval in which recognition of what was happening could have been converted into action. The first scientists reached Lake NYOS within days of the event. Among them were volcanologists, geochemists, and researchers from the United Nations Disaster Relief Coordinator's Office, people trained to recognize the signatures of known events. What they encountered at NYOS did not fit any signature they recognized. The lake's surface was brown, not uniformly discolored. The water had taken on a reddish-brown tone that was most intense near the center of the crater and faded toward the shores. Early samples confirmed the presence of elevated iron concentrations. The CO2-saturated water that had risen from the deep had carried dissolved iron upward, where it oxidized on contact with atmospheric oxygen. The discoloration would persist for weeks. Photographs taken by the initial research teams showed a lake that appeared chemically wounded, its surface wrong in a way that was immediately visible, but not immediately explicable. Water temperature profiles revealed an inversion. Normally, the deepest water in a stratified lake is the coldest. At NYOS, the temperature at depth was anomalously warm relative to surface water, consistent with an upwelling event, a vertical mixing of layers that had previously been separated for years or decades. The chemocline, the boundary between the upper oxygenated water and the CO2-saturated deep layer, had been violently disrupted. Samples from deep water showed CO2 concentrations that remained far above saturation even after the release. The lake had not emptied its reservoir. It had released a fraction of it. The initial scientific discussion divided along two lines. One position held that the event had been triggered by a phreatic explosion, a pocket of volcanic gas or superheated water releasing suddenly from beneath the lake floor, mechanically disturbing the water column and initiating the upwelling. This hypothesis had the advantage of explaining the trigger. Something had to start the process. It had the disadvantage of leaving little physical evidence. No explosion debris was found on the lake floor in initial surveys. No crater within a crater. No evidence of freshly expelled volcanic material that could not have pre-existed the event. The alternative position argued that the release had been spontaneous, a product of the lake's own physics, not an external trigger. CO2 had been accumulating in the deep water for decades, fed by volcanic seepage through the lake floor. At some threshold, a disturbance, perhaps a small landslide on the crater wall, perhaps a minor tremor, perhaps an unusually cold surface temperature altering the stratification, had initiated the overturn. Once started, the process was self-accelerating. Rising CO2-saturated water depressurized, releasing gas, which lowered the density of the rising column, which accelerated the ascent, which brought more supersaturated water into lower pressure, a runaway feedback that continued until the system equilibrated. Neither position could be conclusively proved from the physical evidence available in 1986. What both positions agreed on was that the event belonged to a category that had no name. There was no term in the volcanological or limnological literature for the sudden, catastrophic release of dissolved CO2 from a lake's deep layer. The researchers examining NYOS were not consulting precedent. They were creating it. The phrase that would eventually be adopted, limnic eruption, did not appear in the scientific literature until papers published in the months following the event, as authors struggled to classify what they were describing. The reddish lake sat in its crater surrounded by the dead. The science that might explain it was being assembled in real time, from first principles, by researchers who had not expected to need it. The question that emerged from the initial scientific investigation was not only what had happened, but whether it would happen again. The answer was not reassuring. Volcanic seepage through the lake floor had been depositing CO2 into the deep water for as long as the lake existed. That process had not stopped. Within months of the August 1986 release, measurements showed that CO2 concentrations in the deep layer were already increasing. The lake was refilling. The immediate response from the Cameroonian government was to prohibit the return of residents to the NYOS Valley. Tens of thousands of people had been evacuated from the broader region in the aftermath of the disaster. They were not allowed back. Villages that had been intact, houses, farmland, livestock pens, the physical infrastructure of generations, were closed off. Some survivors attempted to return anyway. The land was fertile, the buildings were undamaged, the grounds required only replanting. The gas was invisible. The risk was abstract to people who had watched family members buried and crops continue to grow. The scientific community focused on a different question: whether the CO2 could be removed. The mechanism proposed was deceptively simple. A pipe lowered from the surface to the deep water, below the chemocline, into the saturated layer, would allow the pressure differential between the deep water and the surface to drive water upward through the pipe. As the CO2-saturated water rose and depressurized, it would release its dissolved gas as bubbles, which would escape at the surface. The process would be self-sustaining once initiated. The degassing water was less dense than the surrounding deep water, creating a buoyancy-driven flow that required no pump once started. The pipe would operate continuously as long as CO2 remained in the deep layer. An experimental pipe was installed at Lake NYOS in 2001. The first activation produced a fountain of water and gas that rose several meters above the surface, a controlled miniature version of what the lake had done on the night of August 21, 1986. The system worked. Additional pipes were added in subsequent years. A similar installation was put in place at Lake Manoon, which had experienced its own smaller limnic eruption in 1984, an event that had killed 37 people and had not been understood at the time as the precursor it was. The problem was scale. Lake NYOS holds an estimated 0.15 cubic kilometers of water. The CO2 reservoir in the deep layer, even after the 1986 release, was estimated at hundreds of millions of cubic meters of gas. The pipes installed by the mid-2000s were removing CO2 at a rate measurably slower than the volcanic seepage was replenishing it in some models. Progress was documented. Measurements taken over years showed deep layer concentrations declining in the sections of the lake nearest to the pipes, but the total reservoir remained dangerous. A single pipe, operating continuously, would require decades to reduce deep water CO2 to levels that could not sustain a lethal release event. There was an additional structural concern that had nothing to do with gas. The crater rim at NYOS, the natural dam that contained the lake, showed evidence of erosion and instability. Geological assessment suggested that a failure of the rim was possible. If it failed, the lake would drain catastrophically, not as a gas cloud, but as a flood. The volume of water involved was sufficient to inundate the Benue River Valley downstream and reach Nigeria within hours. The gas risk and the flood risk existed simultaneously in the same body of water above the same volcanic system that had created both. The pipes continued to operate. The volcanic system beneath continued to function on its own schedule. Lake NYOS holds approximately 0.15 cubic kilometers of water. Lake Kivu, on the border between the Democratic Republic of Congo and Rwanda, holds approximately 550 cubic kilometers. The ratio between them, in volume, in dissolved gas reservoir, in the number of people living on their shores, reframes what happened in Cameroon in 1986 as something other than an isolated regional disaster. It reframes it as a proof of concept. Kivu sits above the same East African rift system that produces the volcanic activity responsible for CO2 seepage into deep lake water. The geology is functionally similar to NYOS at a different order of magnitude. The lake's deep layer contains an estimated 300 cubic kilometers of dissolved CO2 and, separately, approximately 60 cubic kilometers of dissolved methane, a product of biological decomposition in the deep anoxic water. The two gases are layered differently within the water column, with the methane forming its own distinct zone below the CO2-bearing layer. Both are present in concentrations that would be catastrophic if released rapidly. Approximately 2 million people live on the shores of Lake Kivu and in the river valleys that drain from it. The city of Goma in the DRC sits at the lake's northern tip. Bukavu anchors the southern end. Smaller towns and villages line the entire perimeter. The population density around the lake is among the highest in Central Africa, driven partly by the same volcanic soil fertility that characterizes the region, and partly by the lake's role as a resource: fishing, transportation, water supply. A limnic eruption at Kivu, of a scale proportional to what occurred at NYOS, would not produce a death toll in the thousands. The estimates produced by researchers who have modeled the event under various trigger scenarios, various gas release fractions, various wind conditions, consistently produce numbers that are not comparable to any disaster in the documented record of the 20th century. The gas would move into river valleys and downslope gradients faster than evacuation could be organized. The warning time, as at NYOS, would be measured in the interval between awareness and incapacitation. The probability of a spontaneous limnic eruption at Kivu is considered low under normal conditions. The lake's stratification is more complex than NYOS, and the CO2 concentrations in the upper layers, though rising, remain below the threshold for spontaneous overturn in current assessments. But the East African Rift is active. Earthquakes occur in the region regularly. In 2002, the Nyiragongo volcano erupted and sent lava flows into Goma, reaching the lake's edge. The scientific concern is not theoretical. It is that the combination of geological instability and increasing gas concentrations represents a risk that is changing on a timescale shorter than the institutional response to it. Rwanda has moved further than any other government in the region toward a practical response. The Kivu Watt project, operational since 2015 off the shore near Kigas, extracts methane from the lake's deep water and converts it to electricity. A for-profit energy project that simultaneously reduces the methane concentration in the deep layer. It processes approximately 26 megawatts. The total methane reserve is estimated at a volume that would require that extraction rate to operate for centuries before the reservoir approached safe levels. What NYOS established, and what Kivu represents, is that the category of risk called limnic eruption was not a historical artifact. It was an active category. The 1986 event did not exhaust the conditions that produced it. It demonstrated them. The survivors of the Lake NYOS disaster were resettled in government camps. Some were moved to sites in the Womb area, provided with temporary shelter and, in some cases, agricultural land. The resettlement was not well resourced. The camps became semi-permanent. People who had farmed the NYOS Valley for generations found themselves on unfamiliar land, without the social infrastructure of their original communities, waiting for a clearance to return that the Cameroonian government was not prepared to give. Some returned anyway. Through the late 1980s and into the 1990s, families slipped back to their original villages. They replanted. They rebuilt. They understood the gas risk better than any government memo could convey. They had watched it kill, but the land was theirs, and the land was alive, and the lake above it was, on most days, still and blue and ordinary. Authorities periodically removed them. Periodically, they returned. The dispute between the people who had always lived there and the government that had declared their home uninhabitable continued for decades, unresolved. The survivors who stayed in the camps aged. Children born in the NYOS Valley before August 1986 grew up in resettlement. The community structures that had organized life there, the hierarchies, the shared knowledge of the land, the informal systems of cooperation that made farming possible, did not transfer cleanly to the relocation sites. What was lost in the NYOS disaster was not only the dead, it was the social continuity of the communities the survivors had belonged to. That loss does not appear in the official toll of 1,746 confirmed fatalities. The lake itself was not sealed or treated with the permanence the scale of the event might have suggested. The pipes installed in 2001 and after are maintained, but maintenance requires funding, and funding for a lake in rural Cameroon that last made international news in 1986 is not consistently available. Assessments conducted in the 2010s noted that CO2 concentrations in the deep water, while reduced from their pre-1986 levels in the vicinity of the pipes, remained elevated in other sections of the lake. The volcanic seepage had not stopped. The infrastructure removing gas was operating below the rate required to achieve long-term stability in any near-term time frame. The natural dam at the crater rim, the geological feature that holds the lake in place, had not been reinforced as of the most recent public assessments available to researchers. The flood risk that geologists identified in the late 1980s remained unaddressed. Two separate categories of catastrophe potential existed simultaneously at the same site, and the resources directed at the site over the decades since 1986 addressed neither completely. What the Lake NYOS disaster introduced to science, the concept of the limnic eruption, the methodology for measuring dissolved gas in meromictic lakes, the engineering of passive degassing pipes, became a permanent part of the discipline. Papers cite it. Training programs reference it. The event created the scientific vocabulary that allowed researchers to look at Lake Kivu and recognize what they were looking at. What it did not produce was a system capable of responding to the scale of the risk it revealed. The gap between what was understood after August 22, 1986, and what was built in response to that understanding is the actual measure of the event. The lake is still there. The gas is still accumulating. The villages at its edge are still contested ground between the people who belong to them and the invisible chemistry of the water above. The night that ended quietly, no wave, no fire, no structural collapse, produced a morning that has not fully ended.